Alright, so today we are going to be talking about periodicity and looking at the different trends on the periodic table and and what they are and how they relate going left to right and up and down. So first off, valence electrons, you guys probably know what those are. Those are the outermost electrons, and they're the electrons that are involved in bonding. And we'll talk about those in the next unit in more detail. Here he says the periodic table is arranged by increasing atomic number. That was first organized by Henry Moseley in the early 1900s. I want to say 1909 is the date. Unfortunately, he was drafted by the British military in World War I and died. And the good thing that came out of that was the British government passed laws to not draft highly valuable citizens. Not that everyone's valuable, but you guys kind of get what I'm saying. Otherwise, it was arranged by atomic mass. And the problem with atomic mass, let's look at the periodic table here. So, it's argon and potassium dilemma. If you notice, potassium is 39.1 about, but then argon's 39.9. So argon should be number 19, but it's not. So with, what's his name, Dmitri Mendelev's periodic table, he had them ordered mostly by atomic mass, the weight of the elements. But things were weird. Argon was in a very highly reactive group. So if you put all of these in water, it reacts vigorously. And once we get back face to face, we can do some demonstrations of that. Otherwise, I can show pictures, which is not as fun. But so these are highly reactive, and the noble gases, potassium was right here where argon is, highly reactive in a column that's not reactive at all. So that was just some weird things that were messing up the patterns. But then Henry Moseley, this was after the proton was discovered, he decided to order them based off of atomic number of protons. And that fixed the dilemma of argon and potassium being in the wrong spots. And it made the periodic table much more organized in a way that there's so many different patterns that can be seen with it. Right. So, this is some fun history on the periodic table. Vertical columns are called groups or families, and the horizontal ones are called periods or rows. And yeah, we said this valence electrons are defined as electrons in the outermost. S and P orbitals, we got something called the octet rule. They want to have 8 outer electrons. If you got 6 electrons in the P and 2 in the S, you got a total of 8. And is there situations that are more complicated than that? Yes, but that's kind of the simplified general rule. Alright. Yeah, that's where this is. D orbital electrons at time can be considered to be valence electrons, but generally only in bonding practices. Alright. And then here's the octet rule. All atoms want to have 8 outer electrons to be satisfied. So, moving on, we've got electron shielding, and I think this is written down in your packet. So, what is it? It's every time you go down a group in the periodic table, the outer electrons are found in the S and the P sublevels that are further away from the nucleus. The outer electrons are shielded from the attraction of the nucleus more and more as more and more inner electrons lie in between the nucleus and valence electrons. So that's a bunch of words. Let's look at the periodic table. Make some sense of that. So right here is the periodic table, and we're talking about electron shielding being that basically repulsion of the inner electrons, pushing away the outer electrons. So I'm going to draw a little picture of that. Electron shielding, we got the big N for nucleus, and we've got the inner electrons. These are negative electrons, and we got little itty-bitty valence electron over there. And what's happening is electrons are negative and they repel each other. This electron wants to get to the nucleus, but it's being pushed away by the inner electrons. And the thing is, the more and more inner electrons you have, the greater that repulsion, or that push away from the nucleus is. So, and we call that electron shielding, because the inner electrons are shielding the outer electron from the nucleus. So, trend down the group, let's think through this. As you go down the column or the group, we're increasing in our number of electrons. It's getting bigger and bigger. I think this periodic table might have some other, maybe that's a different one I was thinking about, but I think there's an online periodic table that has kind of the electron configuration. Oh, here it is. All right. You can just put that on pause. It'll be about 3 weeks till we find out who wins. But oh, wait, Tommy, I think that's you. Is that you? Oh, there we go.
Sorry about that. Sorry about that.
That's all right. That's all right. So.
Unacceptable.
Unacceptable.
It's webcam Tommy.
Webcam Tommy. Good job.
Good job, Tommy.
Good job.
Got a new computer. Got a new computer.
New computer. All right. All right. Anyways, electron. This is talking about chemistry is way more peaceful. So lowers the anxiety. What we got is inner electrons are pushing away the outer electrons, and as we go down, as you can see, now if I move my cursor, then, oh, there we go. All right, so we got tons of all these inner electrons right here, even more for francium, and hardly any for lithium. So the more and more inner electrons we have, the more and more electron shielding we have. So as you go down, electron shielding increases. I'm going to put an up arrow, and if that's confusing, I'll write the word increases. Trend down. And then as we go across the periodic table, so let's put the periodic table here. Doesn't look like many more inner electrons are being added as we go across. So it's not going to be too significant. So we're going to say it remains pretty constant. All right. Oh, you guys didn't see that, did you? There it is. I wrote down pretty constant. So that's electron shielding. Then we have another concept, increasing nuclear charge. Across a period, the number of shields remains constant. The only thing that changes is the nuclear charge increases, which makes the electrons be attracted more tightly to the nucleus. All right, so what we're saying right here is nuclear charge increases, you go left to right on the periodic table, 1921. So that pull to those electrons increases, and therefore your electrons are going to come closer to the nucleus, which is why the atomic radius gets smaller as you go left to right, but we're going to get to that one in a little bit. We're just talking about nuclear charge. It increases as you go left to right, so that's the simple, well, both are fairly simple, but yeah, trend across the periodic table increases. And then the trend down, you can probably guess it, is increasing because you're going 3, 11, 19, 37, so that nuclear charge is definitely increasing. There we go. Questions so far? I've got a question. How much time do we have? Oh my gosh, 12:35. Okay. Going fast.
We got 15 minutes.
We got
15 minutes. All right, thank you. Moving down to the next one, or flipping the page. Atomic radius. Hey, I was just talking about that. So It says atomic radius is defined as the distance from the center of the nucleus to the outermost electron cloud that is occupied by an electron in the atom. So in a nutshell, we're going to call this VE for valence electron. Atomic radius is going to be the distance, or the radius of the circle if you're talking about it being a sphere or a circle. And this one's fairly straightforward. So if you go on the periodic table, let's do going down first. As you go down, you can kind of see right here, we're adding an energy level, another energy level, another energy level. Now we're adding a fourth one, a fifth energy level, a sixth one, and a seventh one. So that radius is getting bigger as you go down. Oh, whoop, wrong one. Okay, there we go. So as we go down the periodic table, atomic radius gets bigger, and as we go left to right, we're going to see left to right, we have a weird thing happening here. Atomic radius is actually going to get a little bit smaller. And why would that be? It has to relate with nuclear charge. So our nuclear charge is increasing. It is increasing with the number of electrons, but with that greater pull of the nucleus, you're going to have the electrons come a little bit closer to the nucleus, which is why in the fourth energy level, we don't have 4D, we have 3D. So those electrons, those extra electrons and protons are causing the atomic radius to kind of tighten up a little bit. So in a nutshell, left to right, atomic radius gets smaller. It has to do with nuclear charge increasing. All right, then we've got ionization energy. So it's the energy required to pull an electron from the outermost sublevel in an atom. The second ionization energy refers to the energy that would be required to pull the second electron from that sublevel. So if we're going down a group, we're talking about ionization energy. As you go down, the ionization energy actually decreases. The reason being is because electron shielding increases. So if we see francium right here, well, it's not, I think that's cesium, but no, it's barium. All right, but I'm not going to move my cursor, but if you look at the electron configuration, we've got a lot of electron shielding, so that 7s1 electron, outermost valence, it's really easy to pull that one away, which is why francium is the most reactive. It actually doesn't, you can't find it anywhere. It doesn't exist. It only exists in the intermediate state because once it's francium, it breaks down and reacts right away. All right. And then as you can see, the electron shielding decreases, therefore it takes more and more energy to pull that 4s1 in this case, or that outermost electron away. All right, so in a nutshell, as you go down the periodic table, the ionization energy decreases. We got some more trends now. Yeah, we got a few more trends. All right, as you go left to right on the periodic table, the ionization energy is going to increase. Let's see, increase. And the reason that is because you got the octet rule. You got nuclear charge. So as nuclear charge increases, it's going to take more and more energy to pull an electron away from that opposite pole of the nuclear charge, pulling it towards the nucleus. So as you go left to right, it increases. It also gets closer to satisfying the octet rule. The closer it is to satisfying the octet rule, the more it's going to resist leaving the octet rule. So that's another reason. All right, moving on. Ionization energy equation. So you guys probably have seen this, unless I'm having deja vu. But we got sodium plus energy, so you got an input energy to pull an electron away, is going to be Na plus an electron. And typically you would write it as Na Typically it's in the gaseous state, plus an electron. So that's the ionization energy equation. The electron affinity would be the opposite if you're adding an electron. So it is always going to be an endothermic process. You got to add energy to do it. Yeah, there's ionization energies are endothermic. So again, if you're doing like something like potassium, IB is really going to just focus on one electron. So they're going to stay away from like magnesium and oxygen that are working with the transfer of 2 electrons. They're going to focus on the alkali earth metals. Alkali metals, the potassium, lithium, not hydrogen, lithium, potassium, what's the other one? Sodium, and let me just go to periodicity. Let's just show it. There we go. Lithium, sodium, potassium, rubidium, cesium. So alkali metals. IB is going to focus on those. So that's what we're going to focus on in this class. Alright, so if you had gaseous potassium, sorry, we forgot the charge here. It should be positive. It's not turning into sodium, it's going to turn into potassium. Okay. And it's losing an electron. And it's an endothermic process. You got to input energy. Alright. Right here, this is successive ionization energies. Right here, sodium, it's about 496 kilojoules per mole. This amount of energy required to pull 1 electron away, or the outermost. But once you try taking the second outer electron away, it doesn't want to do that. It's too much energy. So it naturally will not do that. And if we look at sodium, the electron configuration is 1s2, 2s2, 2p6, 3s1, I believe. And alright, so the third energy level just has 1 electron, so no problem. It'll get rid of 1. But now you've got 2 and 6, a total of 8, an octet rule. It's satisfied, it's stable. You're going to have to input a lot of energy to now pull an electron away. Same thing with magnesium. 1 electron, not too bad. 2 electrons, just takes twice as much energy. But then 3 electrons, it really jumps. And magnesium is 1s2, 2s2, 2p6, 3s2. So again, in the third energy level, you got 2 electrons. So yeah, 1, 2, no problem. But now if you take the third, you're digging into that octet rule, the second energy level, which it does not want to do. Alright. Moving on, here's a nice little chart. We got ionization energies of the first 20 elements, hydrogen through calcium. So the energy required to take 1 electron away is around 1200 for hydrogen. For helium, it goes up a little bit. Why is that? Well, hydrogen's 1s1 and helium is 1s2. The first energy level can have a max of 2 electrons. So which one is kind of satisfying the octet rule in regards to at least having a full outer energy level? Well, helium is. Can you pull an electron away? Yes, but it's going to take more energy than it is for taking hydrogen's 1 electron away. Because hydrogen's already, it's not a full energy level yet. Going on to lithium and beryllium, we've got the 1s, or actually in this case 2s1, 2s2, same deal going on here. Then it goes down to boron. What's going on with boron? So let's write the electron configuration for boron. It's 1s2, 2s2, 2p1. And then why don't we do carbon 2? We got 1s2. This might pop up in a multiple choice question in May. That's why we're going over it, because it's not enough to just know the general trend. There's anti-trends within the trend, and there's reasons for that. So we're going to go over that. That's carbon, and then nitrogen. This is 1s2, 2s2, 2p3, And then we'll go on to oxygen. It's 1s2, 2s2, 2p4. And then it goes up to fluorine. Why don't we do fluorine 2? I ran out of space. I'm going to put it right here. 1s2, 2s2, 2p5. Let's do the orbital filling diagrams, and let's just do, let's write it all out. Boon's rule, got to fill in 1 electron with each, where you can pair them up. Three of them, 1, 2, 3. And then the last one. Alright, so we're going from, well, first of all, lithium. That's right, lithium. And then beryllium. Alright, so lithium, it's got half a set, so it doesn't take much energy to empty it. But then beryllium's satisfied. The 2s2 energy is filled up, so it's going to take a little bit more energy. That's why it goes up. But now it goes down. So looking at boron, we have the p orbital kind of sitting in there. So it doesn't take as much energy to pull out a p as it does to pull out of a full s, because the p is not full. So it's like, hey, get out of there. That's real easy. So it goes down a little bit. But then it goes up a little bit for carbon. So looking at carbon, because you got 2 of them in there, so now it's not just emptying it, you're just pulling 1 out. So it's going to take a little bit more energy. Same thing for nitrogen. It's already half filled, which is a very stable conformation. If you know anything about curious copper or cray chromium, it wants to be half filled. And then going to oxygen, hey, it goes down again. Well, that has to do with that half filled rule. So this one is actually a lower energy conformation if you pull one of them out and have each of them just half full. Right now you got the first one that's paired up. That's why it goes down in oxygen a little bit. Fluorine, it goes up again because you're still going to have higher energy conformation if you pull one out. And then neon is really high energy because again you're breaking the octet rule if you pull 1 electron out. So main idea, the trend as you go left to right, the atomic, the ionization energy increases overall. However, you have some things that buck those trends, and it has to do with energy levels being half full. So, or in this case, where you have a full energy level right away and you're breaking it. Sorry. Well, that's why it's higher. This one's lower because, it's a lower energy conformation to have an empty and a full s than a full s and 1 electron in the p orbital. So it has to do with the lower amount of energy. It's more stable to have a p orbital half full than partially full or partially empty. Questions on that? Alright, so I think we got just enough time to talk about electron affinity. So electron affinity, I'll just write it down here. As you go down, it decreases. So what is it? It's like the opposite of ionization energy. It's the measure of amount of energy released when an atom gains an electron. The closer an atom is to having a full octet, by gaining an electron, the higher affinity it will have. Alright, so as you go down the periodic table, the electron affinity decreases. So it's kind of like the opposite of ionization energy as you go down. What's the opposite? No, it's the same. So it's the inverse. So if it doesn't take much energy to pull an electron away from francium, then when you add one, it's not going to add much energy, essentially. And then as you go left to right, the electron affinity is going to increase. So again, same trend as ionization energy. Ionization energy increases as you go left to right because of the increasing nuclear charge. And the inverse, if you're going to add an electron, you're going to get the same transfer of energy because of that nuclear charge. All right. There we are. So as you go down, it decreases. As you go left to right, it increases. And here is electron affinity equation. It is, you guessed it, exothermic because energy is being given off. Why don't we do fluorine? We got fluorine gas. You're going to add an electron, and it's going to form Cl minus, plus energy. So electron affinity is exothermic for the first electron. The second electron depends upon the situation. Because there's that gray area of depending upon the situation, you most likely will not be asked, I've never seen it, on an IB test to deal with something like oxygen. You're not going to see it. You might see it as an example question in Zoomdal, but IB is going to focus on the halogens. So, all right, that is it.